Today we're going to talk about the surface area of a sphere, the formula, how to apply it, and where the formula comes from. So if we look at an example, it kind of gives us this little introduction that Cavalier's Kitchen wows customers with volumes of food and fun. This was the headline in the latest edition of Food Critics magazine. When asked the secret of the restaurant's success, head chef and owner Greta stated, "I combine my math background with my love of cooking to create interesting, appealing, and delicious food." Go Greta. Now, one of Greta's specialties is her ability to work with spherically shaped designs. A sphere is a three-dimensional shape such that all points are an equal distance from a fixed point. That fixed point is called the center of the sphere, and the distance from the fixed point is called the radius of the sphere. So just like a circle, a sphere is going to have a center and it is going to have a radius. As we look at the diagram down below, we see that Greta is preparing a cake in the shape of a hemisphere. Now a hemisphere, as we can see off to the side here, is simply the name for one half of a sphere. In this hemisphere, she's planning on wrapping a piece of licorice around the cake, but she wants that to be 4 inches up from the base. So for example, the licorice is going to go around the cake right here, instead of down at the bottom. Given that the radius of the hemisphere is 6 inches, what is the total length of the licorice that is needed? Now again, remember the vocabulary from above. The radius is from the center of the sphere, and it is to the edge, so that radius is 6 inches. But do remember, based on our definition, that that all points in a sphere, all points are an equal distance from a fixed point. So if the radius is 6 inches right here, then any point on the edge of that sphere, if I marked a point right here, for example, the distance from that point to that center would also be 6 inches. If I marked a point over here, the distance from this point to that center will also be 6 inches. So that radius can be drawn anywhere in this three-dimensional object. So our goal is to figure out the length of this piece of licorice that's going to wrap around the hemisphere 4 inches above the bottom. We need to basically take that piece of licorice and spread it out straight and figure out what that length is. So how could we go about doing this? Step 1, let's think about the Pythagorean theorem. Since we've already established that the radius is 6 inches, and the radius could be drawn from the center point to any point on the edge of the sphere, I'm going to draw that radius to right here, and we know that that radius is 6 inches. We also know that the licorice is going to be at a point that is 4 inches up from the base. So from the base, if we go straight up, we know that that's going to be 4 inches. With this little triangle, we can actually solve for this y value. Now keep in mind that the y value is actually the radius of this circular ring. So if we do our Pythagorean theorem, 4 squared plus y squared equals 6 squared, that's 16 plus y squared equals 36, y squared equals 20, and if I take the square root of 20, the square root of 20 can be simplified into the square root of 4 times 5, which means it can be simplified into 2 times the square root of 5. Okay, so now if I want to know the distance around the cake, now remember, distance around the cake, we're talking about a length here. We're going to be finding the circumference of that circle. So we're looking for the circumference of a circle that has a radius of 2 square root 5. Our formula for circumference is 2 times pi times radius. So 2 times pi times our radius of 2 square root 5 will give us a circumference of 4 pi square root 5. Now the length of the licorice then is actually 4 pi square root 5, but that's a rather unusual number. So if I wanted to evaluate that and give a rounded answer, I could put that in the calculator. 4 times the square root of 5 times pi would give us around 28.099, and if I round that to 28.1, our units are in inches, so this would be 28.1 inches for the length or the circumference of that piece of licorice. Okay, let's look at a second example, somewhat similar to that. We have here a sphere with a diameter of 40 feet. Now keep in mind, a diameter is going to be from one end of the sphere through that center point and directly to the other end. So the diameter here is 40 feet. Keep in mind, if the diameter is 40 feet, then that means that the radius from the center to the edge is going to be 20 feet. Okay, now there is a plane that is parallel to the center of the sphere, and it's going to pass through the sphere at a distance of 12 feet from the center. So we're drawing, if we think about this plane, it's going to pass through the sphere. Think of it almost as like a piece of paper sliding through the sphere, and it's going to cut off the top of the sphere like this. What we need to look at is we want to find two things. We want to find the radius of this circular piece of intersection. So we need to know the radius of this. And then once we know the radius in part B, we are then going to find the circumference of that circle, and we're going to find the area of that circular intersection. So in all of these cases, we are looking at this piece right here, and we're trying to find the radius, the circumference, and the area of that piece. Now going back to what we saw before, we know that this piece is going to be 12 feet from the center of the sphere. So we know that this height here is 12. We know that the radius of the sphere from the center to any point on the edge is 20 feet. And I can draw that radius anywhere, so I'm going to draw the radius diagonally up here. Now we have this radius of 20 feet. And then using our Pythagorean theorem, we should be able to find this horizontal distance, which would be the radius of the sphere that we're looking for. So, off to the side, 12 squared plus radius squared equals 20 squared. That's 144 plus r squared equals 400. If I subtract 144 from 400 minus 144, is 256. And if I take the square root of 256, I get a perfect 16. So the radius of that circular intersection is 16 feet. Now to find the circumference and the area, circumference, remember, is 2 pi r, and area is pi r squared. So for circumference, 2 pi times that radius of 16 gives us a circumference of 32 pi. Remember, circumference, like perimeter, is going to be measured in feet. Area is going to be pi times radius squared. 16 squared, remember, was 256. So 256 pi is the area, and area, remember, is in feet squared. Okay, so now let's look at another way to apply surface area of a sphere. Let's return to Cavalier's Kitchen. So it's a popular restaurant with the fishermen. Every day, Greta's staff prepares lunches for fishermen to take on their charter fishing trips down the nearby river. Not only is the food delicious, but the fishermen appreciate that the lunches are packed by Cavalier's Kitchen in waterproof and spherical-shaped containers. The fishermen then tie those containers to their boats and allow them to float along in the water. The food and drinks inside the containers stay cold because the river's primary sources are spring water and melting snow. So what we want to look at is what would be the surface area of one of these spherical containers. Now, where does the surface area of a sphere come from? Here's a little experiment that typically, if we had been in person, we would have been able to demonstrate in class, but this would be something I would encourage you to maybe try at home. In this experiment, what you will need is an orange of any size, pencil and paper. And your first step is to simply trace the orange, draw a circle around the orange. You want to make sure that the radius of the circle that you draw is the same as the radius of that orange. Then you're going to repeat that 4 times so that you have these 4 identical circles. Now do remember that in a circle, the area of a circle, remember that the area of each one of those individual circles is pi r squared. So what are we going to do with those? Well, if you then take the orange and little by little start to peel it, obviously an orange peels into really small pieces often, that's fine. So you're going to peel those oranges into small pieces, actually the smaller the better, and you're going to use those pieces to fill in each of those circles. You really do want to try to fill in so that there's not a lot of space showing in between them, so try to fill it in as much as you can. And when you're done, you should find that you need all 4 of those circles to fill up that orange peel. In other words, it takes that orange peel, it fills up 4 separate circles. So what does that mean? That means that if each of those circles is pi r squared, and we have 4 of them, that means that the surface area of that sphere is 4 times pi r squared. So let's move this little guy out of the way for just a minute here, and let's talk about that surface area formula. So we've just discovered that formula, that formula for surface area, which is 4 pi r squared. Remember, that simply means that that's those 4 circles that we talked about up here when we were peeling the orange. R was representing the radius of the sphere, which was also the radius of one of those circles. So if we wanted to calculate the surface area for one of the spherical containers, if the radius is 8 inches, well, this is going to be a simple plug-in. Our formula for the surface area is 4 pi r squared. Remember, that's just 4 circles. The radius of those circles is 8, so we're going to do 4 times pi times 8 squared. 8 squared is 64, and 64 times 4 is 256. So the surface area of that sphere is 256 pi. Remember, area is squared, so that's going to be inches squared. Keep in mind, we can use the formula for surface area in other ways. So in example 2, if we want to determine the radius of the sphere, whose surface area is 1,256.64 centimeters squared, we can just work backwards. Once again, start with your surface area formula, equals 4 pi r squared. We know that the surface area is 1,256.64, so we can plug in the surface area, equals 4 pi r squared. And then, like we saw in some of the examples previously, if we're trying to solve for the radius, we're going to need to divide both sides by both 4 and pi in order to get the r squared alone. If we do 1,256.64 divided by 4 pi, remember we talked about putting that 4 pi in parentheses. So if we do, 1,256.64 divided by, in parentheses, I'm going to do my 4 pi, close the parentheses, and we get just about 100. Now keep in mind that's representing our r squared, so if we take the square root of that, the radius is about 10, and our units are centimeters. So as we look at one last type of problem, it says each evening the fishermen return to the empty containers to Cavalier's kitchen, and they typically stay for dinner. The restaurant is an interesting structure as it is a hemisphere on a wooden platform. Describe where a plane, in question 3, describe where a plane would have to intersect a sphere in order to form 2 hemispheres. So if we look at, I kind of put a couple of pictures up here at the top for us to be able to look at, of a plane intersecting a sphere. Now keep in mind, back to our very start of the school year, a plane can be kind of modeled with almost like a piece of paper. So think about a piece of paper slicing through a circle. We want to know, in order to create 2 perfect hemispheres, where would this plane have to actually intersect? As we can see from this first picture here, picture A, if the plane slices through kind of toward the top, we're going to end up with a much smaller portion on the top than we are on the bottom. But if that plane in picture B here, if that plane intersects right through the center of the sphere so that it's actually passing through, I'll even mark that, the center of the circle, then it's going to be dividing that sphere into a top half and a bottom half. That circle that's created, this is called the great circle. So it's the circle that's created when a plane passes through the center of the sphere and it intersects the circle and divides it into 2 hemispheres. And the reason we call it the great circle is because it would be the circle with the biggest area that could be formed. If I tried to, for example, if I sliced through the circle, the sphere here, a little bit closer to the top, this circle up here is going to be a lot smaller than that great circle. That great circle is going to have the largest radius, much larger than something closer to the top. So it's called the great circle because it does have the largest area. And that's just a little vocabulary piece of information for you on that. Okay, going back then to looking at if we wanted to, in step 4, if we wanted to write a formula for calculating the surface area of the curved surface of the restaurant in terms of the radius r. Well, remember that the surface area of a full sphere, is 4 pi r squared. If this is a hemisphere, we're going to divide that by 2, which means we could simply use the formula 2 pi r squared for a hemisphere. Okay, so then it says in step 5, let's calculate the surface area of the curved surface of the hemisphere with a radius of 10. Do not include the area of the floor. So if the radius is 10, then the surface area of the hemisphere would be 2 pi times 10 squared, or 2 times 100, 200 pi. Now that we've had a chance to talk about the surface area of spheres and also to calculate some of the circumference and area of different intersections in a sphere, I'd like you to try the homework assignment at the bottom of the notes. Please make sure you submit your notes, completed notes, along with your homework assignment for your lesson today.